Hi everyone, my name is Dillon George and I'm a software engineer here at Facebook. I've been with Facebook for about 2 years now, where I've spent the entire time in the asynchronous computing space working on distributed priority queuing. Today, my teammate Jasmit and I are going to share how we've designed our systems with disaster readiness in mind to offer high availability to the many services which are built on top of our platform. Let's kick things off with understanding why designing for disaster is so important. We'll look at a real-life use case, Facebook's crisis response feature. In the event of a major disaster, like the recent Hurricane Ida, the feature enables our users to let their friends and family know that they are safe, find and offer help, raise money, and get relevant information as it becomes available. As such, it is absolutely crucial that the infrastructure supporting the feature remain available and resilient to disasters itself. Today, we'll be focusing on Fox, a core piece of queuing infrastructure here at Facebook. Fox is a distributed priority queuing service which offers both durability and high availability to its clients. It also happens to be the backing queuing platform for crisis response, along with many systems at Facebook which leverage its durability guarantees to ensure that critical messages are not missed. To understand how Fox is resilient to major disasters itself, we'll first provide an overview of the system to get a sense of what it looks like. Next, we'll talk you through the team's journey to evolve its system to a global architecture with the goal of high availability in mind. Lastly, we'll close things out by sharing some of our learnings and briefly covering some of the challenges that lie ahead. So we know what Fox stands for at this point, but let's dive a bit deeper to get a sense of what the system actually looks like. We'll start with some high-level traits. Fox achieves durability and high availability by building on top of MySQL. The system is currently handling hundreds of billions of items per day and is deployed all over the globe in over 10 physical regions. Given the focus of this talk, it's only natural that Fox itself is resilient to multiple failure domains and is capable of recovering from the loss of an entire region in just a matter of seconds. Moving forward, the content of this talk will be largely centered around the high-level architecture of the system. If you'd like to learn more about the features which Fox supports or its inner workings, I'd encourage you to check out the past at-scale talk titled Scaling a Distributed Priority Queue from the Spring 2021 session. Moving on, let's visualize things a bit to get a sense of what the overall Fox system actually looks like. Producers and consumers use the Fox-provided client to communicate with the backing services which compose the system. Fox leverages an internally developed service known as Shard Manager in conjunction with MySQL to achieve some of the properties which make it highly resilient in the face of disaster. We will refer to some of the offerings from Shard Manager which Fox uses to achieve high availability in later slides. Zooming in a bit, we can see an important aspect of what makes Fox highly resilient to the failure of even an entire region. It's MySQL replication topology. We can see that Fox leverages a replication model where transactions pass through the primary, while data is semi-synchronously replicated to two different physical regions via their bin logs. In this diagram, our primary is in region X, whereas our two secondaries are in regions Y and Z. As with any system, Fox has not always resembled what it looks like today. It hasn't even always had the same properties which make it highly available. Let's now take a look at the team's journey to evolve Fox to meet the demands of Facebook's massive scale while seeking to offer high availability to its clients. Fox's story starts in 2018. It was originally developed to address scalability challenges faced by Facebook's asynchronous computing platform, an internally developed serverless computing platform, which we'll mention several times throughout this talk, is simply async. Toward the end of 2018 and into 2019, the Fox team experienced significant growth and realized that it needed to augment its systems in order to offer high availability in order to insulate clients from the complexities of dealing with disasters after Hurricane Florence caused significant operational challenges for the team. Moving on to 2020, the team established the viability of what it refers to as a global installation for a subset of its customers and kicked off efforts to migrate its largest customer's production use case to a global queuing installation. Coming to 2021, the team has successfully completed the migration of Async's largest use case, which accounts for hundreds of billions of jobs processed per day, to a global installation. We are now actively thinking about the challenges that lie ahead, and we'll speak more on this in later slides. Before jumping into today's world, I'll now hand it over to Jasmit to take us back to 2018 to detail our system's architecture and the problems that we observed with it.
Thanks, Dylan. Hi everyone, this is Jasmit from Fox team. I joined Facebook as an intern in the summer of 2016 and returned as a full-time employee in 2017. Since then, I have been working in asynchronous computing team with the aim of providing solutions to build reliable and scalable distributed applications at Facebook. Outside work, I enjoy playing with my toddler and trying my hands on electronic keyboard. Before we deep dive into our journey, I would like to introduce a few common terminologies we are going to use in today's talk, such as disaster. It is used to describe a natural catastrophe that results into complete region disconnect. And the term drain is used to describe the process of redirecting traffic away from a region. A region is drained either to handle a real disaster or to simulate a disaster for chaos testing. Here is the architecture of regional Fox installation onto which Fox onboarded its first customer in 2018. Fox servers in region X are completely isolated from servers in region Y, and they manage MySQL DBs primarily hosted in their respective regions. Customers use Fox Client to talk to queue servers in the region of their choosing, which then stores items in MySQL DBs for processing. And when requested, the stored items are delivered to customers by queue service. This architecture is simple, horizontally scalable, and supports low end-to-end latency when customers are co-located with queue service. But it is not disaster ready. During a disaster impacting network connectivity in region X, Fox customers lose access to the regional queue service in X. And the MySQL DBs fail over in region Y based on its replication topology. But the regional installation makes it impossible for them to be accessible by the customers. These disconnected DBs are now left unutilized, and the existing items are stuck until network is restored. It means in regional installation, Fox used MySQL replication for durability, but not for availability. Moreover, customers are expected to redirect the traffic away from the impacted region X and redistribute them to other available regions in balanced manner. This means this architecture pushes the complexity of disaster readiness and load balancing to the customers. And now the customers have to incur cross-region latency cost. To summarize, despite the simple as well as scalable architecture and the benefit of low end-to-end latency, the lack of disaster recovery readiness is what makes regional architecture challenging. The region becomes unavailable during disaster, thereby pushing the traffic redirection complexities to the customers, which then leads to high latency. And to add to that, the capacity in impacted region are left unutilized. All of these challenges were faced by Fox team during a multi-day disaster event in 2018 called Hurricane Florence. The team spent a significant amount of time planning manual steps to avoid major impact on customers. I'll now hand over to Dillon to talk about how these challenges are addressed on global installation.
Thanks, Jasmine. Considering the substantial challenges faced by Fox while operating its regional installations, the team introduced global installations to ease many of those pains. Similar to regional installations, Fox customers continue to use the Fox client in order to communicate with the backend services managing MySQL shards. However, some key differences have been introduced. Routing service now proxies queue service, and queue service nodes are globally discoverable behind a single service ID. As such, we're able to capitalize on intelligent routing functionality via routing service and perform what we call following the primary with our MySQL capacity. To illustrate these points, let's look at what happens in the event of a disaster which causes us to lose a region. We'll start with simulating the loss of region X. Similar to regional installations, the queue nodes which exist within that region are no longer accessible, and MySQL shards fail over to their secondary replication regions. However, as we can see, shards which failed over to their secondary regions are almost immediately picked up by queue nodes in the corresponding region. This is possible via some of the global primitives which exist within our shard manager integration, as they enable us to control how our MySQL capacity is assigned in the event of a failover. Internal to Fox, once the shards are picked up, they're almost immediately available for operation. The end result is that items are no longer stuck in the queue as they once were in our regional architecture. So in a global setting, Fox needed a way to handle routing across our global queuing layer. On the NQ and DQ paths, we built two components into routing service which enable intelligent routing, what we call NQ distributor and DQ distributor. At a high level, NQ distributor enables Fox to expose logical region preferences, which can serve as a hint when routing NQ requests to the most geographically optimal shards for our clients. DQ distributor, on the other hand, enables the discovery of ready items across the entirety of the queue layer. The Fox system does not dictate a fixed placement of items for a given topic to a subset of MySQL shards. So it is required that we have a way to discover queue nodes managing shards which have ready items. Let's take a closer look at how the two components behave within routing service to ensure that requests are routed optimally in both standard operating scenarios and scenarios which can cause connectivity losses to entire data centers. We'll start with NQ distributor. In a global installation, a client no longer has the means of specifying the physical region which they are communicating with, like they once did in our regional architecture. In order to continue enabling customers to provide guidance as to where data should ideally be stored, we expose a logical region preference that can be specified on the NQ path. The preference does not guarantee that an item will be stored within that matching physical region, but instead can be thought of as purely a preference that the system will route to the best of its abilities. Let's look at an example using region X. A request will first pass through routing service, where it will leverage internal state to determine how to route the item to an appropriate shard based on the regional preference specified by the client. Upon determining which hosts are eligible for being selected when routing the request, routing service will then direct the request to a queue service node matching its selection criteria. Finally, upon the request landing on a queue service node, it is routed to a MySQL shard which that queue node manages. As we can see, in non-disaster scenarios, NQ distributor enables clients to influence where they would like their items to be placed. In practice, this serves as an important means of placing items nearest to where they'll likely be processed, and thus reduces latencies on the consumption path. Shifting gears a bit, let's look at DQ distributor. Given that NQs are not limited to a subset of MySQL shards, we need a way to discover where items ready to be consumed are. Let's use an example where we have several shards with ready items. Routing service maintains a snapshot of global queue nodes by utilizing an aggregator leaf strategy where it aggregates the state of the queuing layer. Once it has performed its aggregation, it heapifies the data to form an internal priority queue of queue nodes which it uses to route requests. Upon a client making DQ requests, routing service then uses that cache to optimally route requests to the backing queue nodes containing items associated with a given topic ID. In general, we can see that clients are able to benefit from global abstractions which eliminate the need to understand how DQ should be routed. So we have established a sense of how NQ distributor and DQ distributor behave in cases where all servers and shards are in their expected regions. But we haven't seen how they've helped us hide complexity from our clients when failures occur. Let's dive in and take a look at what happens when we lose region X once more. As we've seen before, the X MySQL shards fail over to region Y and are picked up by queue nodes in the same region. We are now in a state where shards which are typically primaried in region X are now primaried in region Y and being managed by queue nodes in the same region. Let's see what happens if a client makes a request with a logical preference of X despite the physical region being completely unavailable. Similar to our happy path scenario, the request will first pass through routing service to build a selection of eligible queue nodes. Routing service's internal cache will indicate that a logical region preference of X has associated shards which are failed over and being managed in a different physical region. That's no problem to our routing algorithm, as it will simply represent the queue nodes from the physical region Y in its selection. Finally, the request will be forwarded to one of the queue nodes managing the capacity which was once primaried in region X, just as if the physical region was still available. So instead of a request for an unavailable region failing outright as it would have in our regional installation, the service is able to automatically redirect requests wherever failed over capacity is available. It entirely abstracts away any notion that the physical region matching a logical preference may or may not be available to our clients. Let's now take a look at the DQ side of things. Despite the fact that shards from region X are in a failed over state, the system behaves exactly as it would in the event of no disaster at all. Routing service continues its aggregation of ready items across all the physical queue nodes which remain available. Since MySQL shards from region X have failed over, The system simply sees those items as being managed by queue nodes in region Y. Similar to our happy path state, routing service is able to perform its heapification of nodes which have ready items and thus route requests based on associated topic IDs. As a result, clients are free to make their requests as they normally would. Once again, clients are entirely insulated from any request routing complexities on the DQ path, and items are never stuck in the queue in the event of a loss of a region. Unlike our regional installations, even if region X is physically unavailable, the items once stored in that region are still available for consumption in a different physical region, and requests for those items are entirely possible. Overall, we have seen that the traits of our global architecture have greatly improved the availability of data in our system. With the introduction of intelligent routing and the ability to follow MySQL capacity, our system can provide high availability to our clients without taking any hits on durability. Additionally, we completely hide the complexities of handling disaster scenarios which once spilled over to our customers in our regional installations. However, as we all know, there are always trade-offs in system design. The introduction of global installations is no different. We've had to deal with the major challenge of discovering items in a massive, globally available system without introducing significant queuing delays. Doing so has proven to be quite the challenge. I'll now hand it over to Jasmit to expand on the challenges the team has faced with discoverability a bit further and close out our talk with detailing what lies ahead for the team.
Thanks, Dillon. To give you an overview of traffic distribution, majority of Fox traffic was supported by regional installation before 2020. Considering the benefits of global architecture of being resilient against disasters, we decided to migrate all Fox traffic from regional to global installation with zero downtime. This effort started with the largest use case of Fox, with the scale of hundreds of billions of items per day, that is, asynchronous computing platform. In coming few slides, I'll talk about the challenges we faced during migration and the approaches we took to resolve them. As Dillon explained, DQ distributor component in Fox routing service is responsible to discover queue hosts with eligible item for discovery. This process is called item discoverability. Before starting the migration, global architecture was validated against only a small fraction of Fox traffic. As the volume increased during migration, we had to scale up both Fox routing service as well as queue service hosts. And the delay in item discovery increased with scale. This was because it was taking longer to refresh the cache in DQ distributor routing service. That means it did not have a real-time snapshot of global queue. We solved this problem by merging old cache with the new one while preserving the learnings from the old cache, such as highest priority item in queue host and the response rate per queue host, etc. This allowed routing service to select top K host by priority from the cache and distribute DQ requests amongst them based on their response rate. However, merging the cache led to having large number of queue hosts in the cache. Moreover, all routing service nodes had the similar cache snapshot. The top K priority selection led to thundering hut for the host in the top of the cache and starvation for the host in the bottom. To solve this, we introduced random algorithm in DQ distributor while selecting queue host from the cache. Instead of selecting top K host from the cache, now it will select the host randomly. With this, all routing service hosts were able to cover all queue hosts, no matter the scale. So far, we talked about technical challenges on global installation. However, the migration itself involved major operational challenges. I would like to talk about our approach of tackling those challenges with the hope to inspire others who might be in process of similar migrations at scale. As I mentioned before, global architecture was validated against small volume of Fox traffic. Before migration, we needed to do load and chaos testing on global architecture in order to gain confidence. For this, we validated almost half of peak Fox traffic through shadow installation and verified the behavior with and without simulation of disasters. It helped us to uncover and fix inefficiencies in our system. We could not test 100% load on shadow because of capacity constraints. The only path forward was to continue with the migration and learn the impact on prod. We needed to get early signal on prod in order to fail fast. For this, we used a flexible config-based rollout mechanism. It allowed us to safely ramp up and ramp back the traffic when needed. This rollout config had knobs to enable the validation of selected workloads on prod. This mechanism helped us to uncover the technical challenges explained in previous slides. Both regional and global installations needed to be active throughout the migration to support roll forward and roll back mechanisms. This means we needed 100% buffer capacity for the period of migration. We understand that it is inefficient and cost ineffective to have 100% buffer capacity, but it was doable with time bounding the migration. The team has come a long way in this journey. More than 95% of traffic has been migrated to global installation and is resilient against disasters. We are excited about the challenges that lay ahead us in order to reach to the 100% mark. The first is supporting low latency workload on a disaster-ready global installation. Video infra is one of the critical use cases of Fox that demands consistent sub-second level queuing delay. And they have ended up building a reliance on regional installation to achieve this latency. However, in global installation, expected events such as MySQL DB failover because of MySQL binary upgrades or regional rain can introduce temporary latency spikes. That impacts video infra workloads. We believe this problem can be solved by further optimizations in ideal data placement and item discovery. Placing the data closer to the customer would help us achieve optimal network latency in global installation. And in addition to that, a deterministic data placement would simplify the item discovery mechanism, thereby reducing end-to-end latency. The second challenge ahead us is further increase in scale, as the footprint of our system is expected to increase by almost 3 times over the next several years. Maintaining current service guarantees with this expansion is going to be challenging. Keeping up with this scale would potentially need capacity-aware routing to achieve better global capacity utilization. In addition to this, we need to ensure there is no regression in item discovery with scale. And for that, we'll need further optimizations to locate desired items in queue faster. If you find this interesting and would like to contribute in solving these challenges, please check out Facebook's job profile for available opportunities. That's all we have for today. Thank you for tuning in.